today's video, we are diving into a crucial aspects of 3D printing bed leveling using Klipper's bed mesh feature. One of the most common challenges in 3D printing is achieving the perfect first layer, especially when your printer bed isn't perfectly flat. That's where bed mesh comes in. It dynamically adjusts the nozzle height during printing to compensate for uneven surfaces, helping you get consistent and high quality prints. In this video, we'll explore what bed mesh is, how it works, and why it's such a game changer for your 3D printing experience. I'll be doing this demonstration on Ender 3 with a rectangular bed, and we'll be focusing on commonly used bed mesh parameters such as probe count, mesh point per segment, mesh fade, and algorithm. There are other advanced options like move splitting, zero reference position, fault region, and adaptive match, which requires a separate video. You all may refer to Klipper's documentation, link in the description. Bed mesh leveling is a method used to dynamically adjust the z-axis during printing. It ensures the nozzle maintains the optimal distance for the print bed, compensating for surface irregularity, which helps to achieve a more consistent first layer across the entire bed. It's important to note that mesh leveling is a software-based correction and can only approximate the shape of the bed. While it improves print quality, it won't completely resolve all bed imperfection. Mesh leveling cannot compensate for mechanical or electrical issues. For example, if an axis is skewed or the probe isn't accurate, the bed mesh module will not yield correct result. This technique is especially useful for printers that require precise bed leveling, allowing them to compensate for uneven or warped surface for better prints. As of recording this video, I am using Klipper version 0.12.0. Now let's see the Klipper website documentation. Once you open the website, click on Installation and Configuration, Bed Leveling, Bed Mesh. You can find the documentation over here. Now let's see the basic configuration for rectangular beds. This sets the speed at which the probe will move during the mesh generation process. Horizontal move Z. When moving from one probing point to the next, the probe will raise to 5 mm above the bed to avoid collision. Mesh min. The first probed coordinates nearest to the origin. This coordinate is related to the probe's location where the mesh probing will start. In this case, probing starts at 35.6 mm from the front left corner of the bed. Mesh max. The probe coordinate farthest from the origin and is relative to the probe's location. Probe count specifies the number of probe points along the x and the y axis. 5 points will be probed along the x-axis and 3 along the y-axis. This means there will be a total grid of 5 by 3 points across the defined mesh area. In this illustration, we can see mesh min, mesh max, and probe count. We have total of 5 probe counts on the x-axis, 1, 2, 3, 4, and 5, and 3 points towards the y-axis, 1, 2, and 3. Our mesh min is the first point, which is here, that is 35.6, and the nozzle will probe towards this direction, the direction where the arrow is shown, and will end up over here, which is the last point, that is mesh max, 240.198. Now let's see mesh_pps and algorithm, which comes in advanced configuration. First, we'll see mesh_pps. The term mesh_pps refers to mesh points per segment. It is specified as an x-y integer pair and also can be specified as a single integer that is applied to both axes. It defines how many points will be measured along each axis x and y per segment. This helps generate a finer or coarser mesh of the print bed surface. A segment referred to a division of the bed area into smaller parts for mesh generation, and increasing this value increases the resolution of the mesh. A value of 2,3 means 2 points will be measured in x-axis and 3 along the y-axis. Higher the value, the more detailed the mesh is, but it can take a longer to complete. Now let's see in this illustration of Klipper documentation. We can see the blue points over here. These are the probe_count points. The green denotes the segment. In this case, you have 1, 2, 3, 4, 5, 6, 7, 8 segments. And the red dot, it says interpolated points. Algorithm. There are two types of algorithm in Klipper. Lag range, which is default, and the second is bicubic. Lag range uses a polynomial based method to eliminate the height between the probe points. It is kept at 6 probe points as oscillation tends to occur with a large number of samples. It's computationally simpler and faster than bicubic interpolation. Works well for beds with relatively smooth and consistent deviation like flat bed or minor imperfection. Bicubic interpolation uses cubic splines to generate a smooth surface. It requires a minimum of 4 probe points along each axis. It produces a smoother and more precise bed, especially for beds with more complex, non-linear surface irregularities. It requires more processing power compared to Lagrange interpolation, which might result in significantly longer calculation time. When to use each one? Lagrange, if your bed is mostly flat and small deviation, or if you prefer a quicker solution with less computation overhead. Bicubic, if your bed has more significant warping or unevenness, or if you want the most accurate possible mesh for first layer precision. Ideal for large bed or those with unpredictable deviation that need finer adjustment for perfect first layer adhesion. Mesh fade. Fade underscore start 1 and fade underscore end 10. This controls where the bed leveling correction starts and stops in Z height range. Bed leveling correction will fade from start of the print at 1 mm and completely stop at 10 mm height. Fade underscore target. This defines the target Z offset that will be used after fading completely, ensuring that no more mesh correction are applied after the fade height is reached. Following is my bed configuration and yours may vary. Do not copy paste the exact configuration that I have. Okay, that was lots of talks. Now let's start. Before we start bed mesh, let's start with screw tilt adjust method, which I had explained in my previous video. It's not necessary, but I prefer to do so. The goal here is to adjust the 4 screws as close to each other, preferably 5 minutes or less. Next, we need to heat up the bed to the normal printing temperature. I print PLA at 60 degree, so I'll set the same. Do not skip this step. Once the bed has reached to the set temperature, proceed with bed mesh calibration. Now let's analyze the height map from Klipper screen. If you see like this, that the entire height map is red, it means the gap between the nozzle and the bed is very less. It's either the bed screw knobs are very loose or the Z offset is incorrect. Adjust the knob first. If no room to adjust the knob, proceed with Z offset calibration. And if the screen looks like this, it means the gap between the nozzle and the bed is too high. Adjust the bed screw knobs. And if the height map looks like this, it's either the bed is warped or need to adjust the bed screw knobs. In this case, the left side is red, which means the gap is less, and the right side is blue, which means the gap is more. Our goal is to have a height map like this. Not necessary, but having like this will have less Z movements. Once you are satisfied with height map, proceed with Z calibration. Do not skip this step. Make sure no filament is oozing out from the nozzle, as this requires the paper test method. Now let's understand the height map or current mesh from Mainsail dashboard. This is the name of the current mesh profile. In this case, its name is default. You can save multiple mesh profiles for different bed conditions or filament type and select based on condition in macro. Size, that is 3x3. This indicates the grid size of your mesh, meaning that 3 points were probed along both the X and the Y axis, resulting in a 3x3 grid, a total of 9 probe points. Max refers to the highest point in the mesh. The value 0.028 mm is the measured height at this location, indicating that this point is 0.028 mm above the reference point. Min refers to the lowest point in the mesh. The coordinate 30,115 represents the X and Y location of the lowest probe point. The value minus 0.020 is the measured height at this location, showing that this point is minus 0.02 mm below the reference point. The range represents the difference in height between the highest and the lowest point on the bed. In this case, the range is 0.048 mm, meaning that there is a total variation of 0.048 mm across the probe bed area. This range is relatively small, which suggests that the bed is fairly level with minimal deviation in height. Now let's see few test print with different height map. Let's see test print with the following height map and range of 0.158 mm. Here is a height map of my next test print with a range of 0.06 mm. Here is the next test print with the bed intentionally tilted with a range of 0.5 mm. Now let's see a test print with the following height map. Here is another test print. Front left, front right, rear left and center. Here is another test print with range of 0.455 mm and algorithm set to bicubic. When I compared the lag range versus bicubic test print, I did not see any difference, probably because my bed is small. Final note, my recommendation is to adjust the bed screw knobs as close to each other so that the bed is as flat as possible, and rest, leave it for bed mesh to compensate. Thank you so much for watching. I would love to hear your thoughts, so feel free to drop a comment below. Don't forget to like, share and subscribe if you found this video helpful. Until next time, I am Remy and I'll see you in the next video. Stay safe and God bless.